Hello, welcome to the first Chemistry 162 video, at least the content video. So this chapter deals with intermolecular forces. But before I talk about there, you've probably heard of the internet. The internet is a connection between networks, and maybe you have or have not heard of intranets. The intranet is a connection within a network, and many places have intranets. University of Hawaii, we have our own intranet, for instance. So, then let me talk about intermolecular forces and intramolecular forces. So intermolecular forces are forces between molecules, and intramolecular is within the molecule. We talked a lot about intramolecular forces before in the last semester, but now we're going to talk about intermolecular forces. So which one is stronger, inter or intra? Well, what's stronger is intra. Intra tends to be much stronger. To give you an example here, we have the water molecule, and the bond distance between oxygen and hydrogen is 96 picometers, and the distance between the hydrogen and oxygen in liquid water is about 300 picometers. So what? Well, you can tell, like, just atoms are a lot like people. The closer you are to someone, the more bonded you are to someone. Like, this is my close friend, and you like give that person a hug. See how close we are. We're very close. So you're like, and if there's someone that you don't necessarily like, or if you're a casual acquaintance, you don't really tend to share space with that person as much, right? The more bonded you are, the closer you are in proximity, generally speaking. Same is true for atoms and molecules. The hydrogen and oxygen are more strongly bonded within the molecule than between molecules, so they're closer. Okay, so, and should be a review for most everyone here. Solid, liquid, gas. Solids are defined by a defined shape and a defined volume. Liquids have a set volume, but they don't have a set shape. Gases have neither set shape nor volume. And what makes a solid strong, the strong intermolecular forces hold the solid together. If the liquid, though, so if you heat something up, eventually the solid will liquefy, and that means that the molecules kind of hang out together, but they're not in a rigid structure. And then in gas, they just fly apart. So the melting temperature and the vapor, the boiling point, so the melting point, boiling point, these are an exact show of how strongly bound something is. So something that has a very low melting point means there's very weak bonding. Something that's a very high melting point means there's very strong bonding. And also, the solid and liquid phases are referred to as the condensed phases, and that's because there is about on the order of 1,000 times as much matter, at least at this temperature and pressure, versus like liquid water. You compare air versus liquid water, there's about 1,000 times as much matter in liquid water. And what brings them together? Why are things attracted? It has to do with Coulomb's law, and I have it right there. Coulomb's law, it's constant, which is 1 over 4 pi epsilon naught. Charge of 1, charge of second over the distance between the charges squared. That is Coulomb's law. The force between two particles is that. So unlike charges attract, like charges repel. And water is a polar molecule. Since water is a polar molecule, there's a slight positive on one end, a slight negative. What do I mean by slight? I mean less than the charge of a proton. A charge of a proton is plus 1.6 times 10 to the minus 19 coulombs. So the charge there on the water molecule is less than the charge of a proton. Likewise, the charge on the oxygen is less than the charge of an electron. And we give it that delta as lowercase delta, that is partial. So I have the first four letters of the Greek alphabet, alpha, beta, gamma, delta. Lowercase delta means partial. Capital delta tends to mean change. And let's start with the simplest types of forces. There's London dispersion forces, sometimes called London forces, sometimes called dispersion forces, sometimes called London dispersion forces. Now they all mean the same thing. The idea is an induced dipole. So if you take something like two xenon atoms, and as they approach each other, you can get a slight change in one, or the electron clouds are going to repel, and you get an induced charge. And one xenon atom will induce a charge, another xenon atom, and then there will be a slight attraction between the atoms that way. And a general trend of this is the bigger the size or the bigger the molecular weight, the stronger the London dispersion forces. So for instance, helium is a small atom. It does not have very many forces, London dispersion forces. As you get bigger, the bigger atom, it means it's more, the electron cloud is bigger, it's more polarizable, it's more fluid. So xenon is going to have a higher force, which means there's going to be a higher melting and boiling point for xenon versus helium. Also, the shape is important. So the closer the molecule is to a sphere, the lower the forces. So for instance, if you look at neopentane, which is a very spherical, it's kind of a tetrahedral structure, versus normal pentane, it's kind of a flat, kind of like a Tylenol kind of structure. It's a very flat structure. The spherical neopentane, close to the spherical neopentane, has less forces than the flatter molecule. So if you imagine this, imagine like two basketballs with opposite types of Velcro. So if you put two basketballs, also opposite types of Velcro, they'll stick, but they're not very strongly tight. Then if you look at like two Frisbees that have opposite Velcro, they'll stick pretty strongly. Why is that? It's because of surface area. So the more surface area, the more polarizability there is, and the most efficient surface area to volume ratio is a sphere. So the less spherical something is, the more polarizable the electron cloud's going to be. Okay, so we've talked about induced dipoles. Now let's talk about permanent dipoles. So dipole-dipole, permanent dipoles. These are not induced. They're always there. Like hydrogen chloride. Hydrogen chloride, because of the bonding, the electrons get drawn towards chlorine because chlorine's more electronegative. So that way there's always a partial negative on chlorine, and there's always a partial positive on hydrogen and hydrogen chloride. So because of that, you get the polar bond, and it's got a stronger attraction. And I'm trying to draw on the picture down there that if you look at the electrons and I put them in as red dots, they kind of flow more towards the chlorine. And a single electron can do this. So if you remember electrons, they can be in many different places at once. So to give you an example of this, we have two molecules, formaldehyde and ethane. They both have a molecular mass of about 30. And the difference is the structure. So formaldehyde has a permanent dipole, ethane does not. And if you see that there's a very marked difference between the boiling point and the melting point, that there's much stronger attraction within the formaldehyde molecule than the ethane molecule. So, and remember, the higher the mass, the higher the dispersion forces. So the dispersion forces are going to be the same for these molecules, but the permanent dipole, that extra force explains the reason why the boiling point is higher and the melting point is higher. Okay, so which of these molecules have dipole-dipole forces? To do this, you have to remember how to do Lewis structure. So carbon dioxide, this is the Lewis structure for carbon dioxide. And it's a linear molecule, and it's nonpolar. So this is nonpolar linear molecule. Carbon dioxide does not. Methylene chloride. So you have carbon, hydrogen, hydrogen, chlorine, chlorine, and then dots around the chlorines like so. And this one does have a permanent dipole. So if you remember, for tetrahedral molecule, this is a tetrahedral molecule, and since not all the atoms are the same, because of that, this one does have a dipole-dipole. Methane, here is the structure for methane. And it is a nonpolar molecule. So this one's nonpolar, NP for not polar. This one's polar. And therefore, the only one that has dipole-dipole forces is B, dichloromethane or methylene chloride. So this one here, if you want to take a look at this and pause the video and think about this, which of the following molecules do not have dipole-dipole forces? So I'm going to look to see which one does not. And the only one that does not is C. Carbon tetrafluoride. Water is bent, it's polar. SO2, that's a bent molecule, that's polar. Carbon tetrafluoride, that's a tetrahedral molecule, but it's all the atoms the same, therefore it's not polar. And D, that's tetrahedral, but the atoms are different, so that one is polar. So the only one that's non-polar is going to be C. Okay, and there's a special type of bond, dipole-dipole bond, called a hydrogen bond. It's when a hydrogen is directly attached to a fluorine, oxygen, and nitrogen atom, and that has a very strong dipole moment. So if you look here, methanol is CH3OH. There's hydrogens around the carbon, but those do not have the hydrogen bond capability because they're not directly attached to an oxygen. The hydrogen directly attached to the oxygen in methanol does have the hydrogen bond, and because of that, methanol is very soluble in water. And so why do we care? It's what keeps your DNA molecule together. So DNA is a double-stranded helix. It's where we keep the majority of our hereditary materials in our cells' DNA. We have other types of hereditary material, not just DNA. Mitochondria, for instance, and proteins are also hereditary material. But the DNA, though, is kind of our primary programming. Excuse me. So adenine and thymine, they hydrogen bond in 2 sites, and cytosine and guanine hydrogen bond in 3 sites. So just sitting there, the DNA molecule will stay zipped, but it's also not that hard to unzip. So that's a nice feature. And then and the enzyme that does this is called helicase. So helicase can go and unzip that. So to give you an example of hydrogen bonds, if you look here, you have ethanol versus dimethyl ether. So dimethyl ether does not have a hydrogen bond because there's hydrogens not directly attached to an oxygen, whereas ethanol does. And you can see that the boiling point and the melting points are also higher for ethanol than dimethyl ether. And remember that boiling point and melting point is a show of how strongly bound something is. So hydrogen bonding, one of these compounds is liquid at room temperature, which one and why? So formaldehyde, there is no hydrogen directly attached to an oxygen, nitrogen, or fluorine. Same thing with fluoromethane. But hydrogen peroxide, though, these bonds here, these are directly attached to an oxygen, and because of that, this one has hydrogen bonding. So that's the one. That's the one that's going to be a liquid. And to look at this more, water is a weird element. It's a weird compound. So that's one thing. Water is kind of, it's a very unique, it's not kind of, it's a very unique compound. Water is strange. Water has a mass of 18 grams per mole, and it's a liquid at room temperature. That's really weird. So if you compare hydrocarbons, octane has got it melts at a lower temperature, but it boils about the same as water, and that has a molecular weight of 114 grams per mole. So compare that to 18, it's a big difference, right? So if you look at this chart here, you have boiling point on the y-axis and molar mass on the x-axis, and you can see general trend is for everything, the heavier it is, the boiling point goes up, but water is a big, strange exception there. So water is very unique, and what's unique about water is the fact that it can give and receive 2 hydrogen bonds. So you compare it to ammonia, so I have a water molecule drawn there. Underneath, ammonia can really only give and receive 1 bond, whereas water can give and receive 2. And because of that, it has a very different, it has a much stronger attraction. Okay, so we've talked about London dispersion forces, then we talked about permanent dipole and hydrogen bonds. What is an increasing strength? What's the next highest one? Next highest one is ion dipole forces. So the polar molecules have a dipole, but the ions have a full charge. So where the dipoles have a partial charge, ions have the full +1, -1 charge. And one only mean by +1, -1, or some like +2. But what I mean by +1, +2, it's +1 times 1.6 times 10 to the minus 19 coulombs. That's the charge of a proton, or negative charge of electron, for instance. And then, so you can see here, the chloride anion has 6 waters around it, and the sodium cation in purple has 6 waters around it. And the idea here is that the attraction in the lattice of sodium chloride versus the 12 bonds here, the 6 from the water and the chloride, and then the 6 from the sodium and the water, those 12 bonds are stronger than the lattice energy of sodium chloride, and because of that, then sodium chloride can dissolve in water. So and also, if you remember solubility rules, it's the big ions and the ones that have small charges. Those are typically the ones that are soluble in water. But here you go. Here's the ion dipole forces, and these are the strongest. So this chart explains the overview of things. So the weakest is the dispersion forces. Then the next highest is our dipole-dipole forces. And then hydrogen bonding is a special dipole-dipole. And then the strongest force there is the ion dipole. And that's just because you go increasingly in charges as you go down there. So that is it for now.